In this video, I'd like to treat an example where an ore-bearing, the log for an ore-bearing clean sandstone has been evaluated. The example is taken from a book by Professor Jurgen, Schon, Basic Well Logging and Formation Evaluation, the first edition of the book. So the goal of this exercise is to get the lithological profile, the description of the reservoirs, compile the input parameters for quantitative interpretation, determine porosity, determine water saturation, derive hydrocarbon saturation at a depth of interest, and determine movable and non-movable oil saturation. So these are two things which are important for quantitative analysis. So in quantitative analysis, there are several reasons why it's important to know the lithology of the zone. One, because the porosity logs require a lithology or a metric constant before the zone's porosity can be calculated. And secondly, because the formation factor used in the Archie's water saturation equation varies with lithology, because the information factor is the inverse of the porosity raised to the power of m, which should be the cementation factor, if I'm not mistaken. The temperature of the formation is also important in log analysis because you may need to obtain the resistivity of the drilling mud and the mud filtrate at formation temperature as compared to the temperature in the lab where it was prepared. Now, input data provided for this exercise is in the table in this view graph. So the mud filtrate resistivity at 90 degrees Fahrenheit, formation temperature, the matrix density, the fluid density, matrix time, transit time, and then the fluid transit time, even though I don't think the sonic log is provided in the tracts. And then very important, the Archie's parameters so we have to assume that M and M are 2. And these are a few relationships that for the exercise would come in handy. Basically, it's the Archie's formula. The water zone resistivity is calculated via two methods, with the use of the SP and then via resistivity through the Archie's formula. In this example, I wouldn't be going through the method to the SP, but notwithstanding, some of these relationships would be used. So this is the log. The original limestone calibrated neutron porosity has been transformed to sandstone reference term neutron porosity. So this can be interpreted as a sandstone system. So let me go through it. So this is the depth track. In track 2, what is termed as track 2 here, you have the caliper and the density correction curve. In track 3, here you have the gamma ray, the SP, and then you have the photoelectric factor curve. In track 4, this is the resistivity curve. So I think the red here is the deep resistivity reading, while the black and green are the medium and the shallow resistivity readings. So you have, okay, the flush zone and then a very shallow reading. Then in the track 5 here, you have the porosity measurements. I think the red is the density measurement, while green is the neutron porosity. Yeah, okay. Didn't even realize that the headers are repeated here. It's important, well, I'll talk about the scales. Now, unlike what was presented in the earlier video, the neutral porosity here is from 0 to zero point 0.5. That's strange. It's usually from 0 to 0.6, and this is from 1.83 to 2.65. The typical thing is 0.0, well, from 1.65 to 2.65. So this is just important to take note of the header information. Then another thing here, there's an error here. This is 0.2 to 200, but actually it is 0.2 to 2000. And this is important noting this. So this is 0.2 all the way to 1, from 1 to 10, from 10 to 100, from 100 to 1,000, and this is 2,000. So this is 0.2 to 2,000, so it's not 200. The gamma ray PI scale is from 0 to 100. Caliper, I think, is 6 to 16. The density correction curve from minus 0.75 to 0.25. So basically, that's it for the scales. So this is just a description, and in most log headers, you will have this. I think the only difference is that the fifth track doesn't reflect here. So just as I mentioned, even though this is track 1, the depth is not considered as a separate track. So so this is just a description of what you have in the different tracks. The sonic log was not displayed in the log taken from the book. So now let's go into the interpretation. So I have reproduced the same log on this view graph. It's very busy, but I would like you to try to follow how I'll go about the interpretation of the log. Now, starting with track 1, where you have the caliper and the density correction curve. The first thing is to check the signature of both curves. You will notice that starting from about, so this is 8,750, 8,760, 70, 80, 90. So from about 8,785 down to the end of this section, you see that the caliper log is fairly constant. However, somewhere between 8,740 up onto 8,800 and 785, the caliper log, so this shows a washed out section. And you'll also see that the density correction curve kind of increases from a very low value here. I think it's just about 0.02. This is graduate, this is about 1. So you can, I think each graduation would go to about 0.1 divided by 10, yeah, about 0.1. So this is 0.25, 0.25. So this is 0.15. This is 0.05. this 0.05, and then this is minus 0.05. So you see that it increases from about 0.05 here. The implication of the change in signatures, the regular signatures here, is that this hole is referred to as a bad hole. Here you had severe washout, and then the DRHO readings here increased greatly. And remember what was said in the previous video about this. So basically, with discountenance, no interpretation, no parameters would be inferred from this section of the whole. So first of all, before you go ahead with any interpretation, you've looked at the scales. The next thing is to look at the integrity of the whole. So from about, for instance, if you're to report, you would state that between 8,740, or you want to say maybe 42 to about 800, 785, that the whole, you have a bad hole because of the severe washout as inferred from the caliper log, and then the increase of the density correction curve from 0.05 or from a very low value to even close to 0.25, which makes the log readings unreliable in this interval section. That said, so we should now recall the steps highlighted in the previous video in going about our interpretation. So the first thing is to define your reservoir and non-reservoir. So the next thing is actually to delineate the log into different formations. So what I have done in the video, you'd see I've used green for shale and yellow. Okay, I have a legend here. So I've used green for shale and I've used yellow for sand. This black is what I refer to as unknown. So you see. So the next thing is, how did I go about delineating these zones? So if you go to the second track has your gamma ray and your SP. And of course, we can use this for shale zonation. So, of course, as we should all know, when you have high gamma ray units, this is predominantly shale. And then you see from about 8,785 down, you're having a blocky sand section, of course, but with some shale streaks here and there. So what we were, in one of the videos, what we're supposed to do is to choose a shale volume cutoff of 50%. And this is what you do. So first of all, you draw your sand line. So typically this is like a modal value, So I have this like a modal value. For convenience, I've just used 20. That's 20 API units. And I've also come to a modal value for the shale line. So this is the dashed line here is the sand line, and this is the shale line. You see that I didn't use the maximum, I've just used like the modal value. This is where you have most of the shale peaks, and that falls to about 80. So what is done there, since we are using a 50% cutoff, so your V shale is taken to be 0.5. This is the gamma ray reading that we want to infer. This is how you are going to draw your cutoff. So this is yet to be known. From the sand line, I have 20, and then from the shale line, I have 80. So using this formula, This is 0.5. This is yet to be known, 20, 80. So this will give you 60, 60. You take this to the other side, this gives you 30, and this comes here, so that gives you 50. So you can draw your line somewhere here. So if you follow it, that takes you somewhere here for the so the idea behind doing this, and even if you increase this slightly to 90, we took this to 90, I think that would take you to about 90 minus 70, yeah, that'll take about 55. Okay, I think I used, so if you use the maximum as is done in some materials, if you use a maximum of, that's 90 minus 20, that would be 70. I take this, that would be 35, that will give you 55 instead of 50. And if you draw it here, so the idea is this: everything to the left here is sand, but what falls to the right is termed as shale. Now, of course, because I'm not putting it, and I'm not using software, I didn't go about doing the shading. So you need to also complement, for lithology identification, complement your shade indicators with your density neutron combination. So what I've done here, if you follow it here, so from the top, that's about 8,700 and 720 up until about 800, 785. This is a shale section. You will also see that within the shale, you're having an overlay, you're having the three resistivity readings overlying each other. This is an indication of shale. Also, if you come here, you see that the density trends to the right of the neutron. Density trends to the right of the neutron. So this is demarcated as a shale zone. Now, if you come further down, this next zone is pretty confusing. So for just clarity, you could have used, this is a very conservative reading. You could have used 90, because you see that you have shale peaks here. If you use 90, your gamma ray reading here would give you 55 instead of 50, and I think that is what I used eventually here. So going back to this, in this section, if you look at it, you're having high resistivity values. Note that the red is your deep resistivity reading and not this. These are shallow resistivity readings. So this is your deep resistivity readings. You're having high resistivity. You're having a zone which appears to be sand, but if you come to the density neutron, you're having very low porosity values. Remember that the values are plotted in such a way that porosity, high porosity is to the left, low porosity is to the right. And these low porosity values are not characteristic of sandstone. So I've delineated this and I've called them black. I've just called them an unknown zone. Even though they falsely present, if you look only at track 2 and track 3, you will think it is a hydrocarbon bearing zone, but you need to look at the density neutron separation to see that these low porosity values are not indicative of sandstone. Now going further down, so we are into the portion that should be sandstone. If you look, you would see that you're having the density and neutron kind of overlying each other, with the neutron tending to be a little to the right of the density. So with good confidence, I picked this portion to be sandstone. you would see the density trending to the right. This is definitely a shale streak. It's very thin, you know, but it's a shale streak. If you move down, you see that the neutron trends back to the right, and then you are having, so this is sandstone. You see, still within the blocky gamma ray section, and here, so this is definitely sandstone. If you look here, which corresponds to the spike on the gamma ray here of values, this is a shale streak here, and this is sand again. You see the density neutron kind of overlying very small separation. And then you see now I'm saying, apart from, I've not inferred fluid content. I'm just looking at the formation. So this is sand. You come back here, you see the density trends to the right, which corresponds to a little increase in your density, your gamma ray values, even though you might still consider this to be possibly probably some shaly sand. And so the identification of the these non-reservoir units within this blocking zone is from the trending of the density to the right of the neutron list. So with this, we've been able to identify shale zones. This is a separate shale zone. This is a thick sandstone with some thin shaly units. And then this is the zone which we've not been able to lay our finger on. So having delineated so first we looked at the integrity of the whole quality. The next thing was to identify the zones. So that done, the next stage would be to look at fluid content and establish contacts. So, we've established that within this zone, that's from about 7,855 to just a little above 8,800. This is non-reservoir rock. So the next thing would be to look at the absolute value of resistivity. Now, you would agree with me that we don't have the typical large separation, which is typical of gas here. But here you would see that you are having some relatively high resistivity within that from 8,800 thereabout up to about 8,840 before your resistivity starts trending downwards. So yeah, so if I remember, after you identified the reservoir and non-reservoir units, the next thing is to identify the water leg. So you see here, the region where I have this within this 32 feet, where I have put this arrow, you see you have like close to uniform low resistivity values. So this is a zone, this is a clear water zone. This is a clear water zone. If you come here, this is another water zone, even though this is quite thin. And you see the resistivity here, quite uniform. Of course, you still have. So between 8,800 and 70, thereabout, to about 8,900 and maybe 15, thereabout, this is a clear water zone. So from this zone, you can now calculate your water zone resistivity, resistivity of the water in the formation. And then this will come in handy. Now, note that I have put an OWC and I have put this with question marks. There's little to establish this claim of an OWC. Even though if you check the interpretation of the Prof in the book, you might be able to infer, but my basis for putting an OW, a possible, and I think it's clear, is better to put the word a possible OWC, is here you start seeing the resistivity drop significantly to a very low value of, I think this is 0.3, yes, 0.3 ohms per meter here. And the likelihood of having hydrocarbons here is very, 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 very low. Very, very low. I mean, from this depth. And that's the basis for me placing the OWC here. You might argue that the separation between you have little or no separation here, even though you have some similar separation here. Yes, you have some similar separation between the neutron and the density, and here it begins to reduce. So on that basis, I put my OWC here. But if I'm going to report, I'll put a possible OWC. So you need information from other sources to ground the presence, whether the OWC is at this depth. But that's what I mean. But I can say that this, without a shadow of a doubt, or at least I can with a high degree of confidence rather, that this is a water zone, and this is another water type. You just have water, this is water, and then you have some shade streaks in between. Now, having identified the water leg and where you are having a possible OWC, another thing that is possible is a transition zone. This point, at least for now, this is so having identified the next thing we need to calculate, make our porosity calculations, and then porosity, and then calculation of the resistivity, the water zone, the resistivity of the water. So if you look at this, you see, so within, so you can calculate the porosity within if you want to check within the water zone. So if you look at it here, so as it was recommended to draw a line in between both the density and the neutron, and you see if you check it out, this would know that this is 0 to 0.5. So this is 0 to 0.5. So this is 0.05. This is 1. This is 0.15. So this is 0.2. And that's the basis for placing this. So the neutron porosity is 0.2. To calculate the density from the porosity, rather from the density, remember that we're giving the matrix density as 0.26, 2.65. This is the fluid density which we're given as 1, and then this is the density, is the average density from this region. So note, I think the range is about 0.82, so you divide that by 10, 0.082, and then you multiply by 1, 2, 3, 4, 5, 6, and then add it to 1.83. That will take you to about 2.322. So if you use this formula, you substitute this, that will give you about 0.19,878, and that's placing the porosity of about 0.2. So the next thing would be now to calculate the resistivity of water, and using this relationship. This is based on the Archie's formula. Since the porosity is 0.2, square 0.2, the resistivity, as if you look at it, basically so this is RT, the resistivity of the true formation resistivity is 0.3. So from here you can obtain what the resistivity of the water in the formation is. And this will give you 0.012. Note that this is particular to the water zone, but you see that here I've been able to report on the quality of the oil, delineate this to reservoir and non-reservoir zones. Okay, I got the equivalent based on the using a show cutoff of 50, and remember what I said about this. Even though it's a very conservative value, I could have as well used 90 here. Then calculated the porosity water zone from both. So even if you find the average of this, you still put you at about 0.2, and then the resistivity of this is the true formation resistivity, this is the porosity using this, and then I was able to get what the resistivity of the water in a zone 100% saturated water is. So what you have here, this highlights the interpretation by in the book. So it says, so here in the first track, they look at the caliper and they saw that there is caliper enlargement indicative of a bad hole. They look at the gamma ray log and the SP log indicates that this section, this section has shale with some stability problems. The correction term for the density derived velocity is very high, and this does not allow any further quantitative density interpretation. So the next thing, this is lithology. I think what is here, in addition to what I have mentioned, is okay. So shale up to 8784 bad hole. Then there's a zone from 8784 to 87995, which is characterized by that correct caliper reading, low gamma ray, photoelectric effect factor of about 5. The photoelectric effect, PEF, is indicative to lithology, and extremely high resistivity, but very low neutron porosity values and very high density. You know, as in both the neutron porosity and the density trend dead to the right, and with low, even though this not doesn't reflect in the logs. All these indications, particularly density, are typical of anhydrite. So this is actually caprock. This was the one which was giving us misleading very high resistivity values. So it had sandstone from 8795 to 810, you know, and with shaley or silty interlayers, the photoelectric factor confirms spots. This you can check up on the photoelectric factor data. The log plot shows neutron porosity column, and this is telling us about the range for both the porosity and base. If you also check it on a cross plot, the points are indicative of sandstone. The following zone is shady sand due to the increase of gamma ray. So this is putting all those plots on a density neutron cross plot. Most of the data points are close to the sand line, which is here, close to the sand line. The data points in the upper right are influenced by the shade section and the caliper, and there are some in the lower. This is indicative of the anhydrite. And so we could check this up. This is giving some more indication to details. So here, the flush zone resistivity is brought into the picture. So it's from depth of 8,800 upwards, resistivity RT increases by a factor of 10. The true formation resistivity is still below the flush zone resistivity. This increase in true zone must have been originated by a decrease in water saturation because porosity is constant. So it's not a porosity effect. And they talked about the probability of the transition zone. So the nearly constant level of the flush zone resistivity confirms reservoir homogeneity and indicates plenty invasion as a result of permeability. I think that refers to this portion. Now, okay, in this class, I wouldn't be looking at show content from. So they went about theirs in a different mode. They picked a minimum. I used a minimum of 20 and a minimum. Even though I couldn't establish this value from below because it was 0 to 100, except the scale they put was wrong. Maybe it was from 120. So this is getting RW from the water zone. So within the water zone, the resistivity is equal to R naught, because R naught is the resistivity of the rock 100% saturated, 100% in water. And this just goes into how and what about the calculation. We'll be looking at RW from the SP. Now, what is left after we've done the qualitative interpretation, which is key for you, is quantitative interpretation at different zones. So table 3, as this table shows, measured data. Now, this data is from the last file, that's the text file, which was plotted. You might see some discrepancies. You may not be able to get this directly from the logs. There'll be some slight differences. So what I have shown in the next few slides is to demonstrate the quantitative computation evaluation at a depth of 8804. Let me show you that depth so that it's plotted. This is 880. This is 8810. So 8804 is somewhere here. This is where I drew the line. So for the show content, you see that 110 is actually an error. This is. So I think I'll correct that in slide. So they use 92 and 16. So know that this is show content at that depth. So let's look at it. Let's see whether the 92. So you could check this up later. I think there's an error with the gamma ray scale, but I'll confirm that later. So here you see that the show content is very low. This is indicative of, so the low shale content is not implemented, know that the linear equation delivers maximum shale content. So particularly for resistivity interpretation, the very low shale content and high water content allows you. The most important thing is the low shale content indicates that this is a clean zone and that Archie's equation can be applied. So this is how this porosity from the density log for the neutron log is just read straight up. We got an average porosity, that's the average of these two. And unfortunately, the sonic log is not was not plotted on, or it wasn't displayed in the plot. So the next thing is calculation of water saturation at that depth. So for the formation factor, this is could have well used the average saturation. That would probably change this slightly. And then for formation resistivity, if completely filled with water, this was done earlier in the slide. So the measured resistivity is distinctly higher because non-conductive oil is present. So here, in the other, in the water zone, the RT was about 0.3, yeah. But here the RT is much higher at 8804. And if you use the Archie's equation, it gives you 0.28. And of course, you can get the oil saturation 1 minus 0.28. And the final thing is to get the non-movable oil in the invaded zone. So for here, you use the Archie's formula, but apply it to the flush zone. So that is done. Formation factor still remains the same. But here, instead of the resistivity using the red line, we use one of the curves just ahead. This is the flush zone resistivity. This is obtained from the mud filtrate. It's obtained from the mud filtrate. And then this is obtained as the flush zone resistivity. So it says the invaded zone is 80% saturated in mud filtrate. That's what this implies. It has displaced the original fluid, but there's still 20% of the non-displaced oil in the pore space. So at this depth, the reservoir has a porosity of 20% and water saturation of 20%. The oil saturation in the non-invaded zone is 72%. So the non-movable oil, the non-movable oil, 1 minus. So the non-movable oil is gotten as 1 minus the flush zone saturation, which was obtained here. So this value is still this value here. So the percentage that could not be displaced is treated as oil that cannot be moved from the vicinity of the wellbore. And then to get the movable, what is done is movable oil is the flush zone saturation minus the water saturation. It's 80% minus 20%, which gives you 52% of the oil there, which is regarded movable. And this brings us to the end of this class.